So hello everyone, I'm Karen from MDPI and I will be your host for today. Thank you all for joining our third session of the 7th International Electronic Conference on Sensors and Applications. The conference proceeding papers and presentations are available on the conference webpage for discussion during the time of the conference from 15 to 30 November. The proceeding papers will be published in the journal Engineering Proceedings. I would like to remind everyone that the session is recorded and that the recording will be made available as soon as possible and will be posted on the conference webpage. Also, want to say that we will have 3 sessions today and each session will be followed by an open discussion. And if you have any questions, please feel free to post them in the Q&A box at the bottom of your screen. And please make also sure to mention the speaker to whom you are asking the question. Again, I would like to start with our first session today. And I would also like to start with Dr. Vallan today. Dr. Vallan is from the University Politecnico di Torino in Italy. And he has received his master's degree in 1996, and the PhD in electronic instrumentation from the University of Brescia, Italy in 2000. And he's currently an associate professor in electrical and electronic measurements with the Department of Electronics and Telecommunications of the Politecnico di Torino. From 2000 to present, he has been lecturing courses concerning electronic measurements and sensors, and his research interests are focused on development and characterization of fiber sensors and measuring instruments for biomedical and industrial applications. So it would be great if we could start with session B, physical sensors entitled. Thank you very much for your presentation and for your participation, and enjoy.
Okay, so thank you for your very kind introduction. Welcome to everybody, and thanks for joining this conference, even though in a virtual way. I'm here to chair the physical sensor session. We have received different contributions concerning sensor for very different physical quantities. The one that we have selected for presentation is based on a particular kind of a transistor that was designed for gas sensing. The paper is titled Impact of the Sensor Temperature on Low Acetone Concentration Detection using AlGaN HEMTs. The presenter is Dr. Ali Ahaitouf, which is from the Georgia Tech Lorraine in Metz, in France. So please, Ahaitouf, you can start sharing your desktop or your presentation. Remember that you have 15 minutes for the presentation, then we have 5 minutes for discussion, question, and so on. Please.
Okay. Thank you very much, Mr. President. Thank you for your introduction. And today I'm going to speak about the impact of the sensor temperature on low acetone concentration detection using AlGaN HEMTs. Okay. During this presentation, I'm going to try to follow this outline. I begin by a context and introduction about the study. I'll present in a second step the experimental results, both at room and high temperature, and it will be followed by a discussion and conclusion. As you know, acetone is one of the most used organic solvents both in the research laboratory, in industry, but most important, it is used as a volatile organic compound which we found in the exalt breed by human. And depending on its concentration in the exalt breed, it can be indicative of some diseases like cystic fibrosis or diabetes mellitus or some other disease. That's why for modern biomedicine, we need highly sensitive sensor for detection of this VOC molecule. Also, we need the development of such sensors for electronic noise development. Among the acetone sensors, we found this structure, which is a high electron mobility transistor, where we have a confined 2D gas here between the AlGaN and the GaN barrier, and it can be easily modulated by the applied voltage between the drain and source, or even between the gate and source. That means that this structure is very sensitive. It is also chemically stable and can operate at high temperature. We can then have a control of this electronic gas by changing the potential applied here, or by changing the charge at the surface of the structure. The first results on acetone detection by this transistor, this kind of transistor, have been reported since 2001 and 2003 by Neuberger and Mehandro and their teams, and they show that the current decrease in the acetone medium in liquid solution. This is an important observation, but later, some recent literature results show that there is an increase of the current instead of the decrease observed at room temperature. But these results have been reported at high temperature, here 200 degrees C, as mentioned here. And here the acetone is used in its gaseous phase, meaning that we don't put the sample inside the acetone, but the acetone is carried by a carrier gas, which is the air here. And now the question is, should we use high or room temperature? If there is an effect of the temperature, how to analyze it? And what is the industrially more appropriate method for this measurement? Those are the questions who motivate our study, and we start to do this development in our laboratory. We then used our own structure. The HEMT structure has been ground on a semi-substrate Fe-doped gallium nitride by MOVP in our lab. The ohmic contact for the drain and source have been designed by optical photolithography and metal deposition. This 4-layer, titanium, aluminum, titanium, gold with these thicknesses, and followed by a rapid thermal annealing. The gate, which is the separation between the drain and source here, is obtained by 15 nanometer deposition of platinum. Of course, the drain and source, there is no difference between the two. The only difference is the bias polarization. And the density of manufactured devices is 16 per 3 millimeters squared. A view of our experimental setup. We have the acetone here, and it is bubbled by nitrogen to be carried out to the sample, which is in this chamber. And the current is measured by the SMU, which is here. We start now by showing our experimental measurements. At room temperature, we observe a decrease of the current, a sharp decrease of the current, and we reach a stabilized value here. Of course, we observe some stabilization of the current here, a few seconds, and it's go down. But when we go back to the nitrogen application, we don't recover the initial value. It needs, as observed here, we need more than 8 hours to reach this value at room temperature. We analyze this measurement and we determine the sensitivity, which is given by the variation of the current over the variation of the concentration, and also the relative variation, which is the variation of the current over the initial value of the current. And at this concentration of 16 ppm, which is small, we measured a sensitivity of 15 microohm per ppm with a time response of 131 seconds. We do the same measurements for several concentration, and what we observed is some somewhere strange. When we increase the acetone concentration, we observe a decrease of the sensitivity, which not expected, because we expect an increase of the sensitivity. Of course, the relative variation also decrease, the time response increase, and this value of the time response is in the range of what we can observe in the literature. Now, when we analyze this measurement, the sensor is biased by a potential, and when we increase the acetone concentration, we also increase the circulating fluxes of nitrogen, meaning that we come with a more important fluxes, which induce some variation of the temperature on the surface of the sample. And when the temperature of the sample decreases, the current increases. And of course, we observe a decrease with the acetone and an increase due to the temperature variation. And there is a competition between these two effects. We don't measure the recovery time because it takes several hours. We decide to go to higher temperature. Here we present only the measurements for 300 degrees C. And we start by injection the acetone during short time. We start by injection during 30 seconds. We observe a sharp decrease of the current, and it stabilizes as you observed here, with a sensitivity of 4.2 micron per ppm, which is smaller to that measured at room temperature, and a fast response time. When we go further, we observe that before stopping the acetone, the current starts to increase, meaning that the temperature effects start to appear here. After a short time, the temperature effects start to appear. When we go for longer time, we observe, just to show you, and when we stop the acetone, we recover the initial value of the current. This is valid for these two measurements. When we go for longer time, the current starts to increase before stopping the acetone. As you observed here, we observed here that the initial value is even exceeded, and the current starts to decrease to reach its initial value after. Meaning that the effect of the temperature is important. It needs a small time to appear and to entirely counterbalance the effect of the acetone. We analyze this measurement, and the most important is to notice that the time before starting is about 20 seconds. We have 20 seconds before the temperature effect, and after that, the current starts to increase. In attempt to analyze what happened, we modelize the decrease of the current due to the acetone a little bit after the temperature effect appears, and we measured a mixed response starting by a decrease and an increase of the current. When we go for longer lifetime, we observe only a decrease of the current, but a huge variation of the current. Remember that when we change the concentration, we change the fluxes coming from with nitrogen, and the temperature effect is more important. In this case, the acetone effect is entirely dominated by the Collin effect. We measure the effect of the nitrogen alone, and we observe that the current, we don't observe the decrease here, but we observe that the current, depending on the fluxes of the nitrogen, the current increase. And these measurements are likely corresponding to what's reported in the literature when they observe an increase of the current under the acetone concentration. That we say that there is an effect of the temperature and a huge effect of the temperature. And when we analyze deeply the measurements of these authors, also, this is only one concentration. We observe that when the current reaches maximum, the current starts by decreasing here. This is a decrease of the current, and maybe when it reached its stabilized value, the effect of the temperature is now stabilized, and the acetone effect starts to appear here. Okay. To understand what happens at the surface of the sample, we haven't any oxygen because we have only nitrogen which carried with acetone. Acetone is a dipolar, is a polar molecule with a moment dipolar. And using the theory of Rabat and Steen, we believe that as our transistor is normally on, meaning that the current at Vg equals when the gate voltage is 0, we have also a current. The surface of the sample is positively charged, and when the acetone molecule comes, they are preferentially oriented with their negative charge going back to the surface. This induces a repulsive action between the molecule of the gas and the gas in the HEMT structure. This induces a variation of the surface potential given by this expression, which is proportional to the number of acetone molecules and depending on the angle between the normal of the surface and the orientation of the dipolar moments. And when this variation, this potential is negative, it appears by a decrease of the current as demonstrated for the acetone case in the literature. This is our observation. And to conclude, we can see that the acetone effect decreases the current at room temperature with a sensitivity of 33 microamp per ppm. This is the highest value ever reported at room temperature for now. At high temperature, there is a Collin effect. The Collin fluxus effect counterbalances the acetone, especially for longer exposure time. And this care must be taken to analyze this measurement. The dipolar moment electrostatic interaction is mainly responsible for the sensor response. And for us, the temperature can be useful only to accelerate the sensor regeneration to go to the initial value, and care must be taken to annihilate temperature response. And finally, I would like to thank all the members of the team, particularly Professor Abdullah Ougazaden and Professor Salvestrini for their fruitful discussion with Yassine Halfaya, and also the funding organisme, la Région Grand Est et le Fonds européen pour le développement régional. Also, I would like to thank the University of Fez for allowing me this scientific stay. And thank you very much for your attention.
Thank you. Thank you so much. We have time for questions. I can start asking something about the gas. You have employed nitrogen to study the recovery time and time constant. What happens if you use air, so that in the presence of humidity or what happens if you use air? So
we don't, for the moment, we don't use air. The same, I think we can have the same thing, but the reaction cannot be the same because I'm going to share my screen. To share my screen again, but the results of San et al. used air, and this is the same trans. This is their results. This is results reported in the literature with the air.
Okay.
We should use air, but to prevent the action of oxygen, because when you have air, you have oxygen, and oxygen reacts with platinum and can induce some other effects. And we first want only to analyze acetone effects.
Okay. And do you control temperature here?
Yes. Yes.
Temperature.
We control the temperature of the sample.
Okay.
And the gas is only at room temperature.
Okay. Okay. And do you think that it's possible to reduce the current consumption I'm thinking about a low power device. Is something of interest?
It is easy to do. It's easy to do because with the applied voltage on the gate, we can use the sensor in its near off regime.
Okay.
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 It is easy to do, and also we can in the fabrication of the sensor we can imagine lower current circulation.
Okay. Okay. We have a question. Okay, so I would like to thank again the speaker. Thank you, Ali.
Thank you very much.
Okay. This presentation concluded this session. Now I see that we have a change.